we're going to start again. And it's still in the 1980s at the moment, but we're going to move from the 1980s up to the present day. And our next speaker is someone who had just left MIT when I arrived. In fact, I think the seat was still warm. But Anthony Beres had worked with the two Bobs together on work in simulation of Bingham plastic that we just heard about in Osman's talk. And Anthony's here from Delaware, flew up this morning, arrived just in time. And Anthony, welcome back. The floor is yours.
Thank you very much, Garrett. I'm really especially happy to be here today to this celebration, very proper for Bob Armstrong. Before I start with my presentation, let me acknowledge my colleague, Norman Wagner, with whom we did the work that I'm going to present to you, which is really an evolution of that Bingham fluid work to bring us to our days. And it's really the work of Soham Jariwala, a graduate student that we co-advise who just graduated last April, and has to do with the rheology of aggregating particle suspensions. But before that, let me say a few words to really give me a great pleasure to be here to participate in the celebration of 50 plus years of contributions of Bob in research, teaching, and service, and contribution that I would like to singularly highlight. It already has mentioned many times. It's the critical participation in this monumental work together with Bob Baird, Ole Hassager, and Curtis in developing this dual really exposure both in macroscopic fluid mechanics and in microscopic kinetic theory of the dynamics of polymeric liquids. And it's really this connection between microscopic and macroscopic that has influenced me the most since the time that I worked with Bob and Bob, and especially the contributions of Bob Armstrong in this microscopic development, whereas with Bob Brown we emphasized a lot more the macroscopic developments and the computational ones. So I want really to bring forward this connection to my most recent work, which has to deal with a different system than polymeric liquids, that of aggregating suspensions, which are very common from drilling fluids to blood, clay, ceramic suspensions, food, and so forth. Really, the key characteristic and connection with polymers is the development of an intermediate mesostructure, which eventually has a lot to do with polymeric networks. And this is one of the contributions in their modeling. But one needs to take into account the microstructure. So this is what I would like to highlight here, and the influence of the microstructure in the development of proper models. And this microstructure can be very different depending on the characteristic dimension of the fractal structure that you end up having in most of these systems, as they tend to aggregate from a more or less linear structure, which is commonly seen with a rouleau in blood, to a planar structure that is seen, say, in aggregating fume silica suspensions to that of a more globular one that you see in carbon black with dimensions going close to 3. So how do you explore these changes in developing a proper framework? These are the examples that I just mentioned, from blood, from fumed silica, all the way to carbon black. Well, that's the challenge, because these structures eventually, as you bring them under shear and in general flow deformation, give rise to non-Newtonian, spectacular non-Newtonian effects, which range from viscoelasticity, shear thinning, thixotropy, and yield stress, or what we call in a single name, thixotropic elastoviscoplastic behavior. Garrett has been also one of the key contributors in theories in that field, and in many fantastic experiments. So how do you make further progress there? From our perspective was to be able to find a proper way to connect structure and rheology within a framework that respects the thermodynamics. The two main ingredients I want to present to you involve, from the microscopic perspective, the use of a population balance approach, where Ramakrishna has been key to develop for many reacting systems, which in this case involves the analysis of processes that generate larger aggregates from smaller ones, as well as they describe the breakdown of large aggregates into smaller ones, probably under the action of the flow. And on the other hand, trying to incorporate this microscopic physics into a framework that is respectful of the non-equilibrium thermodynamics, based essentially on a theory that I had developed after I left MIT, together with my former graduate student, Brian Edwards. He's now a professor at the University of Tennessee, and which we exposed in a research monograph entitled Thermodynamics of Flowing Systems, which appeared in 1994. Essentially, the key component there is the analysis of the description of the dynamics in terms of reversible phenomena, which can be described using a least action principle or Hamiltonian mechanics, and a dissipative contribution, which is described in this level in terms of a dissipation bracket describing the effect of a generalized functional. All right, so let's see very quickly just the schematics of how things work. Offering first what has been done in the last 20 years in the field, which is really basically mostly phenomenological at the microscopic level, trying to describe the changing microstructure through a relaxation equation for a characteristic structural parameter called lambda, typically, which ranges between 0 and 1, 0 describing the completely destroyed structured state, and 1 the fully structured one, having terms which return lambda to its structure form, involving Brownian and shear flow and shear rate contributions, where the primary, those shear contribution coming in breaking down that structure to reduce it all the way down to 0. So coupling this type of a kinetic expression with expressions for the stress that come typically from either the theory of plasticity and from viscoelasticity, many workers and also ourselves with our former student Mwasami, we came up with theories that were pretty good in predicting the behavior of aggregating systems fairly accurately, but with a problem. The problem was that the theory contained too many parameters and was primarily applicable only for shear flows. So if we want to extend it and reduce the number of parameters, this is where the microstructure comes to be of importance. And using the population balance, just pay attention to the fact that there is a fundamental equation that describes the population of every size of aggregate, M representing the number of primary particles that constitute an aggregate. And this expression is an integral one which involves contributions which result either in the restructuring or the breakage of those structures with well-specified kernels from previously developed expressions based on the collisions between different aggregates. So having this microscopic analysis, one connects it to rheology. At the first stage, we did that simply developing expressions for the effective viscosity of suspensions that contain multiple aggregate size, and also evaluating an elastic contribution by connecting an effective modulus of elasticity to the effective volume fraction of the aggregates. As the aggregates have a fractal nature, they tend, when they form, to effectively increase their volume fraction and therefore their impact to the viscosity and rheology. And eventually the shear stress expression is given as an elastic contribution plus a viscous one, with the elastic depending on an elastic strain, which is developed based on a phenomenological equation that is borrowed from theories of plasticity. So with these expressions that were microscopic, but they did have a phenomenological component to restrict them into shear flows, we were still able to come up with significant applications. One of them referred to blood rheology, where, as I mentioned, the aggregates are in the form of rouleau structures, one-dimensional. And here is a comparison of steady-state data for the stress with respect to the shear rate for two different donors. Along the donor experimental data are given by the symbols. The dashed lines show the perfect agreement with the results of the previous theory that I mentioned, which was fully phenomenological. The present one, introducing additional constraints, give semi-quantitative agreement only, but at least gives the promise that this is a way to move forward. We also examine the behavior in transient flows, as for example, the one that you obtain using unidirectional large amplitude oscillatory shear, where you superimpose oscillatory shear with steady shear, and you represent the behavior in terms of a curve that shows the stress versus the strain for different values of strain amplitude and frequency, and one can see reasonable agreement at high values, but some disagreement at lower values in this analysis. So the next level, this analysis here was performed for simplicity by using a coarse level description of the microstructure where all the aggregates were assumed to have the same effective size, which was allowed to vary with varying shear rate. The next evolution was to use this MOMIC approximation, which stands for moment interpolative closure, where we assume a certain distribution of the sizes, in this case a log normal distribution, and we were able to accommodate more faithfully the change in size. We did that approximation for a better behaved system which didn't have all the complexity of human blood, that is that of carbon black suspension. And what we were able to show, as you can see now, is that for steady state data, we are now able to achieve a quantitative fit. And also, what is of importance, of course, the errors are uniformly much lower than the monodispersed previous approximation. And even more importantly, we did generate some data. We had to fit rheology to obtain the best value for the dimension of the fractals. And that fitting value came very close to independently evaluated value through small angle neutron scattering. And this is the detail of the analysis that allows us now not only to see a change in the mean size of the aggregates with increasing CR rate from 5 to 2500 reciprocal seconds, but also a change in the width of the distribution. And this is the most interesting one, this independent agreement now with this more consistent approximation to the results of independent optical experiments. So the structure, because you associate it with something that it's measured, you can independently measure and value the particular model. So this work is now accepted in the AICHE journal and is going to appear in October. And this is actually a story that's going to appear in the cover. Finally, what is the latest development is to incorporate this analysis within a consistent evaluation of the macroscopic equations based on non-equilibrium thermodynamics. I will only get you very quickly through the essence of the theory. It really imposes specific constraints so that in addition of satisfying, of course, the first law of thermodynamics, the constancy of the Hamiltonian, which is the total energy of the system. The entropy generation is always non-negative, and the dissipation reduces with a perfect satisfaction of the Onsager-Casimir reciprocal relations next to equilibrium. The Poisson bracket, you get it by using Hamiltonian mechanics. In particular, you can get it directly from the least action principle. The reversible dynamics, you get it by assuming a symmetric anti-symmetric bilinear form. You start this expression by focusing on a number of variables, which for this system involves certain moments of the distribution and a conformation tensor to describe viscoelasticity. So this really comes along with the kinetic theory that Bob pioneered with describing the effects in polymer fluid mechanics using structure and conformations. And that is introduced into a consistent description of the Hamiltonian or total energy, which involves two terms, one describing elastic effects, the other one mixing effects. And then using moments, we can evaluate consistently those terms and then using the dissipation bracket. I won't bother you with the details. You can find them in this paper that appeared in Entropy last year. But the fact is that there are calculations which you can go through and evaluate the final results. And then at the end, in the final results, many of the parameters now have physical meaning. We can make reasonable assumptions, end up with only 3 parameters to vary, this K and 2 characteristic time constants, and then end up describing thixotropic viscoelastic behavior as an apparent viscoplasticity, as you can see here, because we just wanted to show in this work just a proof of concept, but we describe very important effects that you couldn't get otherwise, genuine non-Newtonian effects, as for example, normal stresses that are grow like the Wasserberg number at high Wasserberg numbers. Forget these low CR8 regime, which is just outside the window that we fit. We only try to fit this part. And then we were able to also describe transients, and I will go very quickly because I don't want to take too much of your time. Also show this hysteresis phenomena. Just want to culminate by saying that with this model now we can move beyond shear flow, describe extensional flow, and an elongational stress that, depending on the parameters of the model, here is how it's predicted to develop over time. So in summary, combining microscopic analysis with thermodynamics, we feel is the path forward to be able to extend microscopic analysis results to arbitrary flows and describe fully non-Newtonian phenomena. I want to acknowledge my collaborators and the funding source, but best of all, thank you, Bob, for an amazing mentorship and your advising that has guided me throughout my career. Thank you very much.
Thank you so much, Anthony. So a great example of volume 2 in application, I think, right there. Our next speaker has a unique claim to fame, I think, that she was an undergraduate in my group and then a graduate student with Bob and Bob. So she really, really wanted to do a lot of rheology and kinetic theory and fluid mechanics. It's great to welcome back Nina Shapley. Mac or PC?
PC.
PC, okay, so you probably Mac.
Okay, thank you. Okay, that's great. Okay. Okay, great. All right, well, it's really a pleasure to be here to congratulate Bob on his wonderful career and thank him for all the wonderful experiences that we've had with learning from him. And so I just wanted to remember back to the 1990s when I was a student with Bob. The Bob Armstrong and Bob Brown group was quite large, around 20 students and postdocs when everyone got together for our group meetings. And the majority of the group were working on the modeling of viscoelastic flows and silicon crystal growth. And then there was a smaller experimental group, which I was part of, studying complex fluids. And so in my PhD from 1993 to 1999, I was working on measuring particle velocity fluctuations in concentrated suspensions. And what I remember about Bob as an advisor and a teacher are many amazing things. So I think most importantly, he has incredible physical insights into many, many systems and really deep understanding. And also I felt that Bob and Bob were a fantastic advising team together, where they both would bring up different ideas and point out different issues in every problem. And I learned so much from both of them together. And I remember Bob being extremely patient with all of our complex experiments and staying calm and being very wise and giving us advice that sometimes it took time to really understand what he was trying to show us. And I felt that he also really promoted a lot of group community and cooperation where all the students would really help each other. And that included diffusing and mediating many conflicts. And one highlight I remember was a course on dynamics of polymeric liquids, volume 2, which was basically the only students who registered for the class were people from our group. And so we had a private class taught by Bob about all the molecular models. And I especially fondly remember the shish kebab model, so which I still think is really funny. So, and then I also really appreciate Bob as a mentor. He had immediate influence on my career with, working on these publications and teaching me so many things and connecting me with a wonderful postdoc opportunity at UC Davis with Ron Phillips, Stephanie Dungan, and Bob Powell, where I learned to apply MRI to suspensions, and I've still been working on that to this day. And also I realized that Bob's ideas have a long-term influence on my research, where it still involves different particle fluid systems and flows. And I really identify with this concept that I learned as a grad student of trying to obtain unusual experimental measurements to test models where that may not be available already. And also, my research has followed a theme of sustainability, which is kind of running in parallel to Bob's efforts in the energy field. And so I just wanted to share a couple of recent highlights that fit in with these, that illustrate these ideas. So here I have some examples of a recent project about suspensions in collaboration with Parisa Mirbad at University of Illinois, Chicago. And what we were doing was we were using MRI to measure suspension flows as the suspension flows through a rectangular channel where one of the walls is a porous medium. And it's very unusual to see people studying the interactions of particles in a flow and porous media. Usually you just see porous media flows or just see suspension flows, and normally they don't mix. So what we were able to see here is if we look at a top view of the channel, or if we look at the flow coming straight towards us, we can see that structures are forming in the particle concentration as we go from a semi-dilute suspension to a concentrated one. And we can see that banding is forming, which is dictated by the spacing of the porous media, since the particles find it easier to move in between the square array of rods than on top of them. Another project that follows the suspension theme is cake filtration of catalyst materials, where that's basically like separating an existing suspension. And this is how catalyst supports are collected after they're manufactured in solution. And so, but with fine particles, as those supports typically are, it's difficult to predict what will happen during filtration. Often it's hard to predict the pressure drop or flow rate, and typically because they're fine particles that can pack so closely together, you have issues with very low permeability. And it's hard to drain the solution out of the cake, and it's hard to wash it afterwards. And so we've been working to try to identify key parameters that determine the filterability of catalyst materials, and also applying non-invasive imaging like nano-CT to characterize the filter cakes once they're formed. And typically they're considered like a black box. And so we're trying to look inside the black box of the filter cake and see what's the structure. And then in terms of the theme of sustainability, I've gotten very interested in the area of water purification. And so we also came up with a particle technology that to aid water purification, where we used naturally abundant polymers like alginate and chitosan that are benign carbohydrates. And they also have a very high affinity for heavy metal ions. And so we make hydrogel particles out of these polymers, and we make aggregates out of the oppositely charged alginate and chitosan, and then we characterize their adsorption properties. So, and then I realized that I've also pursued some industrial collaborations that are related to sustainability, one with a big company and one with a very small company. And with Andrei Potanin at Colgate-Palmolive, we were trying to understand the flow properties that lead to the heel. That's the material left behind after draining a tank. So if you imagine some personal care product like toothpaste or gel or something, or shampoo, in the draining of a tank, we were trying to relate the presence of the heel to the flow properties such as the yield stress and composition. And then with the startup company Nature Coatings, we've been developing high-performance natural pigments, trying to replace existing hazardous or synthetic materials with benign natural ones, but get the same level of performance in terms of binding to a fabric. So those are some themes from my group. And then I wanted to add a slide about ideas about rheology and energy to try to, since Gareth suggested that we should try to connect the morning and afternoon themes. And so I wanted to just highlight a recent project at Rutgers. So I'm actually not part of this project, but I thought this was very interesting that I have some colleagues working on this. So this is it's called RAFT. Basically, it's an array of turbines for hydrokinetic energy harvesting. And I thought this was a very, and the investigators are Onur Bilgin and Roger Wang in mechanical engineering and civil engineering at Rutgers. And I thought that hydrokinetic power was a really interesting idea where basically you're just trying to get energy from a flow of water with no dam or anything like that. And so I guess what I was thinking was, can this idea be extended to low Reynolds number flows, where maybe you can use the unique properties of the low Reynolds number environment, or where you could use it on complex fluids other than pure water. And so I feel that hydrokinetic power hasn't been maybe fully realized, and that it has potential for energy research of the future. And then I just wanted to close with a story. So when I had, when Bob and I would meet to talk about research, when I was a grad student, sometimes I would be explaining some problem with my experiment or some question I had to Bob, and he'd get this really, really far away look in his eye. And I would think, oh no, I'm boring Bob. I'm putting him to sleep. This is terrible. And so I would start talking more and telling him more things about my experiment. And it took me until the very, very end of my PhD to realize that when Bob had that look, he was thinking, really concentrating, and that I should just listen quietly and he would tell me another great idea. So that's what I learned. So thank you, Bob, for everything you've done for me and all of the students, and congratulations. Thank you so much.
Thank you. That's wonderful. He's got that far away look in his eye now, actually. So, okay, sticking with the 1990s, our next speaker is Micah Green, who's, I guess, did you overlap with Nina at the same time? No? What?
02 to 07.
Okay, so we're now up into the 2000s, and Micah's
I got it.
got it. Okay. Moved around a couple of times, but is currently at Texas A&M University, and is going to tell us now, coming back to rods and microstructures, about nanotubes are polymers.
They are polymers, yeah. Thanks, Gareth. Well, Bob, it's great to be here today. It's really an honor to be with this great group. So yeah, I entitled this Nanotubes are Polymers and Other Strange Things That I Learned from Bob. Bob, I don't think directly taught me this. It was one of those things I realized shortly after leaving. As Gareth mentioned, I was one of the later students. I arrived here at MIT in 2002, finished up in 2007. So I have a lot of affection for this particular building over in 66, just a little over that way. And now, Bob, at this point, you must be thinking like, I'm really tired of the old pictures. Do you have any old pictures of anybody else? I do. I do have some old pictures of some other people. So yeah, there you go. There's Bob Brown. So it was great to work with Bob and Bob. I primarily worked on computational work. Several of y'all have referred already to the to Volume 1. Saad Khan had said that Volume 1 of Bob's book with Bob Bird and Ola Hosker. But once you see that Volume 1, you know there is a Volume 2. It does exist. And so that's where I ended up actually spending a lot of my time, was in Volume 2. I was in one of those classes similar to what Nina talked about. And when I first became interested in Bob's group, even before I arrived at MIT, he emailed me an early version of this paper. Now I need you to imagine someone who's not yet a graduate student trying to read this paper and just saying, how many words into this paper can I get before I say, I don't understand what's going on anymore. And one thing I've kind of realized over the years is that the American education system is not always very good at like teaching us how to think about an equation. The American educational system says, equation, start with equation, plug in numbers, get answer. Or here's equation, derive thing, you're done. And it was Bob who helped me to look at an equation like this and really understand it. By the way, I originally was very worried. I was like, should I really put an equation in my presentation? And then Jeff presented earlier. I'm like, never mind, I feel much better now. So, oh, by the way, before I go on from the book, Stephen Hawking famously said when he published A Brief History of Time in 1988, he wanted to put a bunch of equations in there. And they said, hey, for every equation you put in your book sales are going to drop by 50%. So let's do the math of like what the book sales are on these two. Like, too many equations. So I will go back to this equation. And one of the things Bob helped me to see is like, okay, look, let's break this equation down to where it looks like something that you recognize. This is a diffusion type equation. So I see F. What is F? F is like the probability that you find a particular rod at a particular place with the center of mass at a particular place and with a particular orientation. So if you just look at this term here in red, you could say like, okay, del dot something del. Okay, this kind of looks like an equation I know. That actually looks similar to like an equation you might see in your mass transfer class that says, okay, what does concentration do? It spreads out, it minimizes gradients. This is the reason that none of us are worried that all the air molecules in the room are all going to go to the top half and leave the bottom half, right? The air molecules are going to tend to spread out. And what you see here next in blue is you have a very similar kind of term, but instead of del squared in space, this is basically del squared in rotation space. What this means is, just like those gas molecules are evenly dispersed throughout the room, if you have a bunch of toothpicks, now Brownian toothpicks, mind you, right? So these are Brownian, and if you just dump them on the floor and let them wiggle around, they will generally have an even distribution of orientations. So being able to physically picture that takes it from being like just a math problem and turns it into something that actually has a physical meaning. I feel like I wasn't very good at that until I learned that from Bob, that you can't just look at it as this is just a math problem. You have to have a physical intuition behind it. And this is actually why chemical engineering is a valuable degree, right? There's lots of different people out there who can solve math problems or plug numbers into an equation, but a chemical engineer being able to look at an equation and say, there is a physical reality that I recognize behind that is what makes it valuable. And my work in Bob's group largely focused on not just these terms, but also these kind of green terms here. That term there in green is a potential, which means that these rods have the ability to interact with each other. So normally entropy says be randomly oriented, right? There should be no preferred orientation. But if these rods begin to interact with each other, they will begin to be oriented in somewhat the same way, just as what you see here. And so this is what we mean when we use terms like a liquid crystal. Right, a liquid crystal, it is a liquid, it does flow, but there's a preferred orientation. There's a crystalline order to it, and so it has both liquid and crystal characteristics. And that's what an equation like this would describe. And figuring out the numerics behind simulating something like this was tricky, and so that's largely what my PhD focused on. Toward the end of my PhD, I was getting close to done. I had made the decision to go into academia and become a professor. And I was talking with one of my lab mates, Tice Clark, right? Tice actually, I texted with him this morning. He sends his regards and his congratulations, Bob. And Tice asked me an annoying question. He said, oh, you're going into academia. So nano or bio? And I was like, Tice, that is really rude and really ill. Like, just because I'm going into academia doesn't mean that I'm going to go into one of these hot areas of nano or bio. You shouldn't say things like that. And Tice said, nano or bio? And I was like, nano, shut up. And so indeed I did go into the nano, and so I went much more toward carbon nanotubes. And so you may think like, well, that seems pretty far away from what you were doing here at MIT, but like, take a look at those nanotubes, right? Why are nanotubes a big deal? It turns out the synthesis of nanotubes had actually been going on for a long time. Why were nanotubes and other nanomaterials identified in the 90s? It's mostly just because our microscopes got better, right? The microscopes got better so we could actually see what we were doing. And at some point, I kind of made this realization of like, that's kind of a rigid rod polymer that has a very high persistence length. It has a repeat unit, right? This is what we call an armchair. Let's see if I can get this to work. There we go. We call this an armchair nanotube. You see how there's kind of an armrest and then a seat and then an armrest, and that's the repeat unit. So that makes this nanotube metallic and conducting in nature. But this is effectively a conducting polymer because it has a repeat unit. And it turns out that once you start treating nanotubes like polymers, a tremendous number of advances can begin to happen. I actually wrote a review article during my postdoc at Rice University on exactly what happens when you start to treat nanotubes like polymers. It turns out you can say, how do we process rigid rod polymers like Kevlar as liquid crystals? You can process nanotubes the same way. So I did a postdoc with Matteo Pasquale at Rice. Matteo, here he is. He is actually a Minnesota product, which I know many of you in the room have connections to Minnesota. So Matteo is one of Bob Brown and Osmond Bosseron's academic brothers. And Matteo is one of the people who said, a nanotube is a rigid rod polymer and you can actually form liquid crystals. You can actually form liquid crystals of nanotubes. These are nanotubes in chlorosulfonic acid under cross polars. And the reason you get this beautiful structure is because exactly as the theory predicts, the nanotubes will form these liquid crystalline structures. It turns out nanotubes are actually a better model molecule than tobacco mosaic viruses or any of the rigid rod polymers we had worked with in the past. And so the reason I started working in this area is I met Matteo here at MIT. He gave a seminar, and the idea of saying this kinetic theory, like what we see in Bob's books, plus nanotubes, we really need to bring those two areas together because nanotubes are actually the perfect molecule to apply that theory to. You can see that even in SEM images like what you have here on the bottom left. The other interesting thing you can do with nanotubes is you can actually, some single-walled nanotubes fluoresce, so you can watch them. You can actually watch them move around. So here's a video. This is a little nanotube moving around. Looks like a rigid rod polymer. You can see it bends slightly. And so it turns out there's all kinds of theories that you can actually test because you can track the nanotubes. You can watch how they bend. You can even watch how they diffuse. You can see that it diffuses along its length much more easily than it diffuses in a perpendicular fashion. And so another student in Matteo's group did a lot with this, and I'm proud to say that she's actually here in the room with us. Nikta Fakhri is here at the back. She's now a professor at MIT. And what's amazing is she used fluorescence imaging of nanotubes to go back and test theories about polymer dynamics that had been formed in the 70s, right? But it was like, now we have an actual model polymer we can look at and watch how these things move and watch how they diffuse, and actually showed which of these theories from the 1970s, work of Dijen and others, would actually apply. We also applied these same kind of concepts to rheology of nanotube suspensions. So sometimes you can get a little too deep into all the equations and you get to the point where it's just a math problem. But what you have to remember is the idea of ultimately there is going to be an experiment that measures the rheological behavior of these suspensions. So most of us are familiar with shear viscosity, shear measurements. But you can also do extensional viscosity measurements. Gareth has done a lot of work in that area. And what's interesting is using kinetic theory, you can say, if I have a suspension of Brownian rods, can I predict the behavior, the shear rate dependence of the shear viscosity and the extensional viscosity? How does that relate to the length of the nanotubes? You can come up with equations that actually show, if you make the nanotubes longer, here's how that will impact their extensional viscosity behavior. And if you have that equation, then that means you can actually measure nanotube length with your rheometer. And you think like, is that good? Is that good to use a rheometer? Wouldn't it be better to use a microscope? When you use a microscope, you're seeing a few dozen nanotubes at best, whereas you're seeing trillions of nanotubes in their collective behavior and the way it cashes out in their rheological behavior. So we got to the point where we could measure the extensional rheological behavior of nanotube dispersions and the shear rheological behavior of nanotube dispersions and back out the nanotube length. Isn't that amazing that you can do bulk rheological measurements on a big giant rheometer and back out nanoscale quantities? But that's what theory allows you to do. Just to continue on to some of the work that's going on in my own group, one of the things we've become known for at Texas A&M is using electric fields on nanomaterials. It turns out nanotubes heat up like crazy in response to electric fields, and that turns out to be really useful for lots of practical applications. But one of my students also noted recently, said there is some stuff in the literature on how nanotubes will actually align in response to these electric fields. And so he did a series of experiments where he showed, yes, the nanotubes will align in response to the electric fields, but they also heat up. So if you have the nanotubes in a thermosetting resin, like epoxy, you actually have a race. Which one will win? Will the nanotube be able to align? Or because it heats, will it cure the polymer around it and lock itself in place? And depending on how you tune that electric field, you can see both behaviors happen. The reason I care about this so much is because of the 3D printing work that we have going on. There are a lot of rheologists who are focused on 3D printing right now. One thing I can tell you is if you're trying to 3D print thermosetting resins, it's kind of a pain. It's like imagine trying to make a tower out of toothpaste, right? As you build the tower up, eventually it yields under its own weight. And even if you manage to get your tower of epoxy to hold, you go set it in the oven and you begin to heat it up to cure. And what happens to the viscosity as you heat it up? The viscosity goes down, then it begins to cure, and then it goes back up. So to get around those problems, we used electric fields, not just to align, but to heat these nanotubes so that as you print, it cures the resin. So instead of like building this little tower and hoping to God that it doesn't fall down, you print a layer and then use the electric field, cure a layer, print, cure, print, cure, print, cure. And you can print virtually any thermosetting structure you can think of using that technique. That paper should be coming out fairly soon. But more important than any of the technical things that I got to discuss with Bob, Bob was really a mentor to me in terms of my career and work-life balance and things like that. Those of you who know me know I have a little bit of nervous energy sometimes. I'm a little bit of a nervous Nelly, as my father would say, and I was nervous about the prospect of going into academia. I mentioned this to Bob. I thought like, getting an academic job is scary. The tenure clock is scary. All these things are scary. And as y'all know, Bob is a pretty low stress individual. And he told me something, and I'll never forget it. He said, Micah, what you should do is you should work on the problems you think are interesting and important. And in terms of like the time that you have to put in and work-life balance, you should work how much you think is appropriate. And if that doesn't get you tenure, then you don't want to be there anyway. And at the time I thought, easy for you to say, very easy for you to say. But now that I've been through a lot of this, I now see that he was right. And part of what he was communicating along those lines is he's saying, the work is not something that we do to prove that we can do it, to prove that we're smart, or to build up our own value and identity. That's not what the point is. The reason we care about our research is because it's a beautiful, wonderful opportunity that most humans will never have. Most people will never have the opportunity to do the kind of research that we do, to learn the things we learn, to meet the people that we've met, and write equations down. Most people never get this opportunity. And we are born at a particular time in history where we have this unbelievable opportunity. So the reason that we care about our research is not because it determines our value as a person, but rather because it is a great joy and opportunity. And I try to communicate that to my students day in and day out. So with that, Bob, I want to say congratulations. I'm really excited to be here and glad to be a part of this great community. Thanks.
Some very wise words indeed there for people in the audience thinking about academic careers. So we've come all the way from the 1970s, where we began this morning, to the 2010s. And our last speaker this morning is Safar Jamali, who came to be a postdoc through the MIT Energy Initiative with Bob and I. I think it was our last active collaboration. Came from a degree in Case Western, came here for 2 years, 2015 to 2017. And he's going to tell us a little bit about his work on applications in the energy area, in particular work that was funded at the time by Chevron. And at the end of this, before we break for lunch, a request would be for all the students in the audience who have worked with Bob to come down to the front, because we'll have a little photograph with everyone as well. Safar. As we're setting this up, I'll just point out that, of course, nano or bio was the words that maybe were the questions when Micah and Tice were around. Now it's machine learning or data-driven are the words that we'll use now. And I think Safar's going to tell us about that.
Thank you, Garrett. So yes, this is an honor to be able to speak here. I represent a great body of postdocs who work with Bob over the years, and so that's amazing. I'm going to talk about data-driven rheology and the M word, machine learning in rheology. So looking into the future, Garrett mentioned Bob has always been big on what's new, what is the latest technological advancement, and so I'm hoping this is more of a futuristic view into what is next in rheology, or at least what I think of it as the new thing in rheology. But we won't get there until before, without looking at where things start. And the birthplace of machine learning, any data-driven technique, is computational side of things. And so I'm going to try to be brief, but this is a brief history of computational rheology. A while back, I was asked to write a viewpoint for the Rheology Bulletin on data-driven rheology. Me being out of my depth, I emailed Bob and I asked, well, can you tell me a little bit about the history of computational rheology? And so this is interesting. Late 1920s is the birth of rheology, right? The name rheology was coined, but in 50s and 60s, FEM, molecular dynamics, the new, any numerical technique for that matter, really showed up. But in 70s is the first time early developments by a lot of people in the rheology community started being developed. Tanner, Crochet, Caswell, Walters, Gary Lee, and of course Bob. That's when Bob started working at MIT, right? And so 1979, this is where Bob pointed me at, was the very first international workshop on non-Newtonian numerical methods in viscoelastic fluids in Rhode Island, and Bob was one of the contributors. One of the very first papers that used numerical techniques in rheology was in 1981 out of a master thesis of Michael Mendelson here on using FEM for viscoelastic fluids. About 9 years later, to my knowledge, is one of the very first real one-to-one benchmarking and comparisons between numerical solutions and experiments, again, out of Bob's group. And in 94, the very first numerical rheology track at the Society of Rheology meeting was held. Guess what? Bob was the president of the society then, and the technical organizer for that meeting was Anthony Barris. So you can see the connection, right? And today, numerical simulations, larger scale simulations, numerical techniques have become a major pillar of the rheological sciences in general. And that's all really made possible by laying the foundations by Bob's group and Bob's work over the years. And now, if I move forward and show you a few examples, the rate limiting factor in computational science is becoming what they are today to us in rheological science has been the computing power, right? So this is from that 1981 paper. You can see the resolution, the type of meshing that you're looking at. 9 years later, you got to a much better one. And today we're looking at systems in very fancy numerical techniques like adaptive length scale for viscoelastic fluids. So obviously computational capabilities have really advanced tremendously over the years. In terms of particle simulations, this is early works that John Brady did started at MIT actually on Stokesian dynamics. That's a scale of what you could model with these particulate systems. But then, this is sort of, yeah, so you can see the movie. This is the work that actually we published, the sort of work that I did with Garrett and Bob. And I believe this was probably one of the latest rheological papers that Bob wrote, right? So now with that, I'm going to show you a little bit about the history of data-driven and statistical methods. Well, in 1960s, linear regression models and statistics in rheology also started showing up. And before 1970, 1967, deep neural networks were already a thing. So why this hasn't become a thing until very recently? Well, because of these two, right? One was we weren't really able to store or handle large amounts of data. Two, There was no clear pathway to put in the physics that we believe in into our neural networks or machine learning platforms. And this all changed very recently in 2017 using a method called PIN, or physics-informed neural networks. I won't get into details of that, but well, I finished my work with Gareth and Bob in 2017, so you see where this is going. That's where I started my job at Northeastern. So I started thinking about, okay, what could be next? And I'll get back to that, but I'm gonna draw a parallel here. So no matter if you're thinking about computational or data-driven sciences, you always start with an observation. This is an example that fluid mechanicians love, flow past a cylinder. In computational science and engineering, what you do is you take a model that describes that phenomena. For example, that could be Navier-Stokes, your conservation laws, what your equations of interest. What you do is you discretize that equation over a certain domain using polynomials, different weight functions, you name it, and then you pick a numerical solver to solve it for that particular flow problem using, the methods that I already mentioned. In data-driven sciences, you can still use the same model. So the guiding principles, the physics is still exactly the same. Instead of discretizing it, you represent it through different methods that are data-driven. For example, neural networks, transformers, graph. And then you, instead of numerically solve it, you use inference models like Bayesian inference or maximum likelihood. And that allows for solution of that particular problem. Now, again, the key is there, right? To be able to use the model or put the model into your machine learning platform. So really, the key is to make sure our data-driven tools respect the physics that we want to respect. Again, that has been at least fundamentally done in that 2017 paper, showed that you can put in different differential equations into neural networks. And I started basically doing the same thing for rheologically relevant equations. So you can do that implicitly through what we have done, we call multi-fidelity neural networks. We work with Procter & Gamble in trying to go from formulation in Head & Shoulders shampoo to what is the rheology in 2 years. So we actually reduced the design cycle for P&G from over 2 years to about 2 months. And that's real money for industry, right? You can put in, again, your equations explicitly in physical form, and then you can basically couple that with your conservation equations and make predictions of any flow field that you want for non-Newtonian fluids, for any arbitrary geometry that you want. And then later, what we showed was that you can actually mix these two approaches, implicit and explicit physics, to build the next generation of constitutive equations. So this is a piece of that work. This is the model that Gareth is developing in his group called isokinematic hardening for these thixotropic elastoviscoplastic fluids that Anthony also mentioned. We showed that you can actually mix those type of equations with actual experimental data. And I'm going to fast forward to make predictions. You won't see two distinct lines. The green here is the neural network predictions of a very complex fumed silica gel under a wide range of parameters. And the black is actually experiments. So you're mixing physical laws that you believe in with a very few experimental measurements, and you make predictions that are really, really accurate. Some other work that we have done in the field are, for example, you can let the data choose the model, right? Instead of choosing the model yourself, you can let the data choose the model. You can do any differential equation. This is a recent work we did in using neural networks to solve fractional differential equations. Those are not easy to work with numerically. And we recently published a guideline to data-driven rheology in general, how other people can pick it up and actually do this in a user-friendly way with rigor and robustness that we expect from any tool in that area. This is the very recent work we've done. Again, my take on this one is, for example, how can we put the material in the driver's seat instead of deriving our considered equations ourselves, let the material tell us what the equation should be. And it turns out you can. So this is the experiment on a carbopole solution. This is what our rheology-informed neural networks picked out from 2 sets of experimental data in terms of a model. So they construct a very new considered equation that is this, and this is the best considered model out there. So you can compare how well this neural network that is injected with the right rheological information does. So very quickly, I'm just wrapping it up. To me, data-driven rheology is the immediate future of this field, at least, extension of computational work. And again, I'm trying to follow the footprints of what Bob had done in 70s and 80s in laying the foundation step by step to make sure that these computational tools are not used in rush and that they're built in a robust way and reliable way. But I think these are key for the next maybe 10, 20, 30 years to bring together under an umbrella of, this is my term for it, rheology-informed neural networks, but data-driven techniques may just be the tool that bring together theory, experiment, computation, everything in a seamless way. And you can do model detection, characterization, you can go from formulation to rheology, and then you can actually do complex flow modeling with those. With that, I'm gonna acknowledge my group and my collaborators, but also a very special thanks to Bob. I just listed 3 things here, and this is a little personal, but so Bob, you remember the first day I got here to start my postdoc, my very first meeting, said, well, this is the first time you're meeting. Nice to meet you, Bob. And he goes, well, bad news, your project just got canceled. So we're gonna have to find another funding source for you. So me being naive and desperate, I started, throwing out ideas over the next couple of months. Can we do this? Can we do that? And then at some point, he sat me down and he goes, stop. I'll take care of you, right? But remember, you're not going to do a project or any scientific pursuit just because you have to. Do something that you're proud of 5, 10, 15 years down the road. And that stuck with me, right? So he taught me you have to always pursue. So Micah was absolutely right. This is a privilege to do this job, but you have to always pursue what is meaningful, not what is expedient. I was going through some personal stuff at a time, and he taught me that mentorship goes beyond science. It's always personal. Everybody here, I'm sure you have had personal experience that Bob was the most supportive person around, right? And I've been lucky to live in Boston, not to go far away. And he also showed me that mentorship never ends. I've been lucky to just drop a line, stop by and have a lunch and just pick his brain up. So for all of that, thank you, Bob. And what you will see in a second, and Garrett, it's right over there, is this legacy is huge. So together with Garrett, we tried to put the RCA academic family tree. So Bob, please. So what you're seeing here is over 500 names of Bob's students and their offsprings. Bob, your legacy lives on. I don't know if this is on, but anyway, most of those major branches are present here, but this is huge and a testament to an amazing career. Thank you, thank you.
Thank you. Do I get a chance to?
You absolutely have
Or
to.
you want to finish that, or?
No.
I could go on and on, All right. So I have to say a few things. So one is just an observation that came up a number of times during the morning, and started with reminded initially by Osman. And that's the incredible impact of students on our system. I get asked this question, particularly now that I'm in energy. I get asked, aren't the national labs just as important and contribute as much to innovation as a university like MIT? I ask as a rhetorical question, and I sort of disappointingly come back with the answer, absolutely not. And the difference is that MIT has students. And the students, you, form this constant flux of young, fresh talent, new ideas, new ways of looking at the world, happy to challenge the way we're used to thinking about things. And out of that comes innovation. It's really, really important. So I said, Osmond sort of opened my eyes to that in my second year here. I have this student in the undergrad fluid mechanics class come up after class and say, he'd like to do something more in research on fluid mechanics. And I was a little skeptical, but we started a project, and lo and behold, first paper that I wrote out of MIT came out of this undergraduate collaboration. And maybe a fresh way of thinking about the opportunity in front of me at MIT with the kinds of students that we bring in. So it has been absolutely wonderful to see this display of what you've done with what you've learned here, but what you've learned in many other parts of your lives as well. And I'm just extraordinarily proud of all of you and what you've done. Second thing I just have to mention is that also noted in quite a few of these presentations is a collaboration that was game-changing for me. And that was maybe, I think, towards the end of my first 10 years here, or 7 years here. What was, I worked hard to help recruit Bob Brown to come to MIT from University of Minnesota, where he was a graduate student. And that was just a spectacular collaboration over my whole career here until Bob finally moved across the river. And actually, I remember with Micah, who was still a student at the time, we had a few meetings in the president's office over at BU. I think maybe for Micah a little bit intimidating, but in any case, it was just a terrific collaboration, and my life here wouldn't have been the same without it. So thank you all, and I'm just really in awe of what this family tree has done. So thank you.
All right, thank you so much, Bob. The sessions will continue this afternoon at 12:45, so we have a relatively quick time for lunch. For the students, there's the bag lunches, box lunches are at the back there and spread out around here. But anyone who worked with Bob or who thinks their name is on this family tree through one generation or another, please do come down to the front. Bob Brown too, and we'd like to get a picture of everyone if possible. Thank you all for this morning's session. Thank you.